Good afternoon, good morning, or good evening, distinguished colleagues, partners, and guests. My name is Jim Curlin. I'm the head of UNEP Ozone Action. And for those of you who don't know us, we are one of the implementing agencies of the Montreal Protocol's Multilateral Fund. So it is my great pleasure to welcome you to today's webinar, which is organized jointly by the International Institute of Refrigeration and Ozone Action. This collaboration reflects our shared commitment to advance sustainable refrigeration solutions and to support developing countries, which are known as Article 5 parties, under the Montreal Protocol and its Kigali Amendment. So our aim is to ensure that the national ozone units and their stakeholders are well informed about the new developments across the cold chain sector and that they are empowered to make decisions that align with their national environmental and economic priorities. So today's discussion will share insights from the latest IIR and UNEP cold chain technology briefs. These briefs, which are authored by eminent experts, are designed to be practical tools for capacity building and to help inform the policy developments so that the national ozone units can navigate the evolving refrigeration landscape and enable them to steer their countries towards sustainable, low GWP, and energy efficient technology solutions. UNEP Ozone Action's long-standing and excellent partnership with IIR brings together technical expertise and global experience, ensuring that the information that we share is scientifically robust and tailored to the needs of the Article 5 countries. So through the combination of IIR's research leadership with Ozone Action's Montreal Protocol compliance support, we're providing actionable knowledge that strengthens the implementation and accelerates the transition to climate-friendly solutions. So today we will explore refrigeration solutions at every scale, from residential systems to large commercial applications. And we'll examine emerging technologies such as solid-state refrigeration that promise to transform the sector. So by sharing and fostering dialogue among experts, industry leaders, and policymakers, we aim to accelerate the adoption of solutions that support compliance with the Montreal Protocol, but also food security and climate resilience. So thank you all for joining us online in this first webinar, and your engagement today is vital to strengthening the cooperation and ensuring that the Article 5 countries have the resources and the knowledge needed to meet their obligations under the Montreal Protocol while advancing sustainable development. So thank you very much. Welcome to the webinar, and over to you, Sahir. Thank you.
Thank you very much, Jim, for setting the stage and for highlighting the importance of the cold chain and the important role of the scientists who are today our keynote speakers. And we'll be speaking about residential small-scale refrigeration with Professor Zhong, then large-scale supermarkets refrigeration with Riley, and then Katya to speak about emerging technologies. Before we move into the agenda and the speakers, I would remind our participants, thank you for joining again. You will have the chat box, the Q&A for any questions. My colleague Nella, she will be supporting you, and we will be collecting the questions for this Q&A session after the speaking slots. Now I'll give the floor to Professor Zhong, who is Professor Ji-Hwan Zhong from, he's the president of IIRB2 Commission from the Republic of Korea, and he will be speaking about refrigeration in homes and small commercial settings, focusing on energy efficiency and climate considerations. Professor Zhong, the floor is yours.
Okay, hello. Thank you, sir. Hello, everyone. I'm Ji-Hwan, and I'm going to talk about the household refrigeration system, actually the refrigerators and freezers. Okay, so everybody maybe heard of cold chain. So cold chain is stages that refrigerate the product pass through from the producers to consumers. Actually, the later stage of the cold chain, in this right-hand side view graph, you will show the background in pink. In that stages, we need various refrigerating equipment to keep the refrigerated food below 5 degrees C and frozen food in below -18 degrees C. So to achieve this kind of goal, we have various kind of refrigerating equipment, and it can be classified into 3 different categories, like commercial and professional and domestic refrigeration. My talk today will be focused on the household refrigerators and freezers. Okay. So maybe many people may heard of the global manufacturers of refrigerators like Samsung, LG, Whirlpool, and Panasonic. There are many the leading companies across the globe, from the Asian countries and European and Northern American as well. So the left-hand side of the bar chart shows that on average, usually 200 million units of refrigerators are sold out globally. So every year, 200 million. So it makes so many the refrigerators and freezers are in operation at this moment. So depending on the data source published by the IRR in 2024, so number of refrigerators and freezers in operation was 2.2 billion globally. So which is huge number actually compared to the other systems like commercial refrigeration systems and refrigerator transport system as well. So 2.2 billion refrigerators keep running 24 hours on the whole year. So that's why even individual refrigerators consume around 30 watt or 40 watt. But globally, there are too many. So that's why it consumes huge amount of electricity and energy. So left-hand side pie chart shows that it shows the residential energy use in United States. So it shows that refrigerations consume the 5.7% of total energy of the residential, and freezers 1.3. So totally 7% of residential energy is used by the refrigerators in US. But this kind of number is dependent on the social and natural background. For example, the right-hand side table shows that average household electricity consumption in Korea. So you can see that in refrigerators is ranked 5th. So it accounts for the 9.8%, almost 10% of electric power is consumed. An interesting thing is that below that refrigerator, we can see that kimchi refrigerators. So every meal they eat kimchi. So every house have their own refrigerators dedicated to kimchi fermentations and distillation. So it consumes another 4.5% of electric power. So maybe in other countries and in other societies, maybe they may use a different kind of version of the refrigerators. So because they consume a huge amount of electric power, every countries have their own energy leveling programs. These energy leveling programs contribute to significantly reduce the energy consumed by the domestic refrigerators. So right-hand side, you see that there are various versions of leveling systems. The IEA report shows that this kind of leveling systems made the freezers consuming electric power decreased by an average 2.3% per year. This is very the important numbers. Actually, the leveling systems programs really contribute to reduce the energy consumptions. So because of the energy leveling systems, the manufacturers, I already mentioned the 11 top players, and every companies manufacturers are trying to develop new technologies, a new design of their refrigerators to improve their energy efficiency. In terms of energy efficiency, if I break down the system that can contribute to energy consumption, the first one is the refrigeration cycle itself. So new design of new cycle types, new economizer systems they're developed. And compressor design, condenser and evaporators, both are heat exchangers, and they are trying to develop new design of heat exchangers to reduce the energy consumption by due to these heat exchangers. And also insulation is very important. Insulation block the heat load coming in, infiltrating from the room. So all insulation is very important, and also operation maintenance. I'm going to show you just a couple of examples of what kind of research activities are being on the way. The first one is that the cycle, the refrigeration cycle itself. It shows there are 4 different design configurations of systems. The left-hand side one is the conventional one. Usually, refrigerators consist of 1 compressor, 1 condenser, and 1 evaporator. However, usually the refrigerators have 2 different compartment. Basically, one is for refrigerating compartment, the other one is a freezing compartment. So it gives a different level of temperature environment. So when the single evaporator is used, they need some kind of ducting system to distribute the cold air to the higher temperature compartment, I mean the refrigerating compartment. So because of the temperature, the level is different, the efficiency of the refrigerating system can be changed. So the right-hand side, the most right-hand side system configuration gives the independent 2 refrigerating systems are installed in our refrigerators. It's usually called the dual loop systems. So each individual cycles are supplying the refrigerating effect on the refrigerating compartment. The other one is the freezing compartment. So by doing this, so the recent research shows that the implementation of this kind of configuration gives a 12% reduction of total energy consumption. 12% reduction is a huge contribution, actually, considering that 2.2 billion refrigerators are working at this moment. So the other one is the compressor itself. The compressor is a workhorse of the refrigerators. It provides a refrigerating effect. Actually, there's a power of which can circulate the refrigerant and generating refrigeration effect. So recently, many companies, manufacturers are trying to develop some linear compressors to improve the efficiency. And also they are trying to develop technology that can operate without oil. So they say this is oil-free compressor. So if we implement oil-free compressors, it can contribute to improve the heat transfer efficiency of the heat exchangers. So I mean, the both evaporators and condensers, they can performance can be improved. So the size can be reduced, and the COP, I mean, energy efficiency can be improved. So let me show you some recent research. So one of my colleagues tested that kind of oilless compressor. So the data, the plot on the left-hand side of the plot shows that the energy consumption of the conventional refrigerators, and the other open symbol shows that the refrigerator equipped with oilless compressor. It shows that the energy consumption is reduced significantly. So that kind of the new technologies can improve the energy efficiency. However, whenever we develop new technologies, there are some hurdles or challenges we have to improve further. Okay. So as Jim mentioned initially, the reason we are working on is that to reduce the effect to the environment. So fortunately, the refrigerators usually use the low GWP refrigerant at this moment. For example, many other heat pumps and air conditioning systems use various kind of HFC and HFO, many different versions of refrigerant. But in refrigerators, domestic refrigerator usually operate on R600A. This commercial, the material name is isobutane. So isobutane is a natural material. So 75% of refrigerators are working on the isobutane, and the other 25% is working on R134A. So usually that refrigerant is used in the Northern American companies because of the kind of regulations. Anyway, recently the United States government and the research bodies announced allowed to use that isobutane. So I guess in the future the portion of isobutane will be more and more increased in globally. So it means R134A has global warming potential of 1530. It's very high. But as I mentioned, isobutane is a natural material, so GWP is 3, so it's very low. So maybe we can contribute by changing the refrigerant to the isobutane. So lastly, I want to just simply mention another kind of refrigeration technology as well, because the reason we are worrying is that when the hydrocarbon and the HFC materials are released to the atmosphere, it will impact on the global warming and something. So if we don't use that kind of fluid, instead if we use a solid material, we don't need to worry about that effect. So magnetic, the solid state cooling technology also has been developing, but it's not mature yet. So it's not ready to replace conventional systems. However, for the specialized or niche applications, for example, at the right-hand side, the slide shows that kind of home wine cellar. This is built using the thermoelectric refrigeration systems. Or some kind of different versions, or niche applications are already they make use of this kind of solid state cooling technologies. So that's kind of technology, the development are being on the way to improve the energy efficiency and reduce the environmental impact. Okay, let me conclude my remarks. So, conclude my talk. In the domestic and small-scale refrigerations, energy consumption is a primary concern rather than the fluid itself. So the R&D activities are in progress already globally. So maybe in the future I can expect more and more better and better the energy efficient refrigerators will be released. That's it, my presentation. Thank you very much for your attention.
Thank you very much, Professor Jong. Thank you for the very important insights and speaking about the small scale refrigerators. Now we move to our second keynote, who will be Relay Bradley Barta, Assistant Professor for the Mechanical Engineering at Purdue University at the United States of America, and he will be speaking about a large scale supermarket refrigeration system and the transition to low GWP refrigeration systems and refrigerants. Over to you, Riley.
Great. Thank you very much for the introduction there. So as was said here, I'll be then diving into large scale and supermarket refrigeration to give a short overview there. To touch on some of the background here, a lot of our work focuses largely on the refrigerants, equipment, and system design and control sides. So we do some thermophysical property characterization, transport property, and then a lot of mechanistic modeling. And a lot of this resonates a lot with what Ji-Wan just mentioned in terms of if we have a system that uses environmentally friendly working fluids, but we can't do so efficiently, such that when we don't have a perfectly renewable grid, then we're just kind of taking CO2 from one pocket and putting it in the other. So I was very excited to have the chance to speak today because it aligns very well with work that our group does at Purdue. For a background to the energy consumption side, large scale and supermarket, right? Many of us know these are quite significant energy consumers, but the numbers themselves are quite impressive, right? So looking at supermarkets around the world, looking from 40 to 60% of the electricity use in supermarkets can be attributed to refrigeration. And of course, as these supermarkets grow in size, that becomes significantly more relevant in food service in general, right? So not just supermarkets, but industrial kitchens and so on. Approximately 15% of that energy in food service buildings, according to the EIA, goes towards refrigeration. And then you see a significant amount of energy per year from the European Commission there. So these are certainly relevant areas to focus on, and that's how we want to focus on the combination of direct and indirect emission reduction. Right. So if we look at some of the measures that we can let's say implement to reduce this overall energy consumption, they range from thermodynamic to quite practical. Right. So installing doors and efficient lighting on cabinets. It seems maybe trivial, but it's a significant benefit that can be realized somewhat easily. Of course, the thermodynamic side, looking at upgrading the refrigeration system with overfed evaporators, parallel compressors, and so on and so forth. Integrating with renewable solar energy and thermal energy storage systems have significant benefits, but there are only a handful of those, largely due to cost. And then looking at integrating these systems with heat recovery. So depending on the infrastructure surrounding the system itself, this can be done quite effectively. So on the right-hand side, you see an example of a transcritical CO2 system, which often, if they're, let's say, just a four-component cycle, can struggle to meet these coefficient of performance of hydrofluorocarbon or hydrocarbon systems. And you see this system on the right has a range of bells and whistles, and this was presented at a couple of ICRs ago in Montreal, where they were talking about actually using this system and commissioning it in the Middle East using expansion work recovery from multi-ejectors, flash tank bypass with parallel compression, and so on and so forth, such that even using transcritical CO2, they were able to achieve a competitive COPs, right? Which is a case study that very much solidifies the fact that if done correctly, transcritical CO2 can also be a competitive system. If we look at food service establishments in general, you see here that the distribution between condensing units, process chillers, and storage cabinets is quite relevant. There's not necessarily one weakest link, if you will, but they're all, let's say, need to be addressed somewhat in parallel. Ji-Wan did a nice job of introducing some of the energy labels around the world, which is really cited as a very key aspect of reducing this overall energy consumption. If we can bring in some degree of uniformity around the world in terms of, or even for specific regions, to saying this is the minimum required or allowable, this is something that's been proven to be very powerful and continues to do so, for example, in the EU in 2015 with their eco design. Additionally, again, from the practical side, a lot of this really doesn't have to do with science itself, rather things like implementing planned and preventative maintenance of equipment, right? So much energy can be consumed from systems that simply aren't operating as designed. And that's something that needs to become, let's say, more and more present, if you will. Moving slightly away from the energy perspective and thinking about the effectiveness, right? So at the end of the day, the primary job of the cold chain is to make sure that food gets from the production to our tables, right? So thinking about food waste and food going bad just in general, display cabinets can actually be one of the weakest links in this, which you wouldn't necessarily think is the case. But it certainly has been proven that 7 to 35%, for example, of supermarkets do not maintain the right temperature in refrigerated and frozen foods. This can then, of course, compromise food safety, reduce energy efficiency, and be a challenge for compliance. And these regulations, shown here in the middle column, are associated then with, let's say, the equipment and food safety temperatures shown on the right-hand side. And while that may seem like a large margin, for example, 0 to 5 or -5, depending on the region, capturing uniformity, especially without a door, is even a challenge that many manufacturers today struggle with. We've had discussions with with manufacturers in the last year or two that talk about if you put a piece of meat with a thermocouple in it in the back versus the front of a cabinet, how much of a difference that will make, right? It's quite measurable. So again, these types of practical issues that have very real implications also need to be addressed. Moving forward, right, another aspect of what we wanted to touch on here and what the brief definitely dives into a bit is the refrigeration transition. Of course, this is happening at different rates and with different orders of magnitude around the world, but the general trends are somewhat uniform. And that you're seeing a transition from hydrofluorocarbon to some combination of hydrofluorocarbon, hydrofluoroolefin, as you see in many R54, I call them X because the C and B are both being used somewhat often. Mixtures that you see quite a lot in North America. You're seeing more and more centralized CO2 systems for commercial refrigeration. I have a couple examples of that, but even through discussions that we've had with relevant OEMs, they'll say in Central and Northern Europe, for example, they don't really sell anything but CO2 systems to supermarkets these days, right? So this is a very growing field and will only continue to do so. Slightly less common, but certainly still relevant, are the hydrocarbon secondary loops, which is to say you're having a large central hydrocarbon refrigeration system, and then you have a secondary loop to reduce charge and make sure you don't have A3 working fluids near your customers, right? That's something you're seeing a lot of with both propane as well as 1270, less at the latter, but nonetheless relevant for volumetric heat capacity reasons. And then from a professional standpoint, you see a lot of propane. Right, G1 also mentioned isobutane or 600A, and then those same HFC, HFO blends. Right, so if we dive a little bit deeper, specifically into hydrocarbons, right? We mentioned that there are some centralized systems with hydrocarbons, but we're actually seeing a significant number of 290 systems that are standalone display cabinets, both with and without doors. Those numbers themselves are growing tremendously around the world. From the latest ATMO report, you're seeing on the order of or several million in Europe. And even in North America, which is generally a bit slower to pick up on broad and hydrocarbon trends for a variety of reasons, you're also seeing a non-trivial number of these systems pop up. There has been a lot of progress there in terms of charge limitation increases to systems, for example, I think 350 grams with doors, 500 without, and that allows you to get a quite meaningful cooling capacity out of a well-designed system, and that allows quite a broad acceptance of this. And depending on systems, right, if they're centralized, less so, as I mentioned earlier, but you're seeing a very broad acceptance and interest in these standalone hydrocarbon systems. And with that being said, right, we mentioned the CO2 challenges at high ambient temperatures that can be, let's say, addressed with the efficiency increasing measures. Hydrocarbons generally don't have that issue, right? They have their own challenges largely associated with practical or slash flammability issues, but thermodynamically they're quite powerful, right? So that really hasn't been the problem with hydrocarbon. Rather, it's been a challenge to get them into buildings safely, or rather to have the safety standards to allowing them to do so. And then, of course, creating enough or producing enough equipment, which in the last few years has really also been addressed by the market to make sure that we have adequate compressors to build such systems. A couple of large examples here. On the left-hand side, you see a 4 megawatt cold storage facility with pure CO2 systems, right? 5 racks, 65 compressors, right? So quite a beautiful example. This photo was then from a few years back from an article there. And on the right-hand side, you see a distributed propane system. So one of those centralized systems that I mentioned don't happen all that often, but certainly exist. And what you have here is basically you have the separated R290 system here in the top half or top upper right-hand side, a brine to chiller heat exchanger, which is to say that the secondary fluid is then a brine in this case, that then is transferred to the display case lineup such that that's where the heat is then absorbed into the brine and then rejected into the system, such that A, you can keep your refrigeration system charge quite low, and B, you keep the customers separated from A3 systems. A key point here is the latter system, right? You see the citation there. It's from 2003, right? And the key there is that this technology has existed for quite some time. It's been investigated by researchers all over the world, but now it's just starting to gain more and more traction. So this is a standard example, but I wanted to also make sure I highlighted that this has also been looked at before. Now we're just seeing broader acceptance, largely due to hydrofluorocarbon phase outs. Another example here of a cascade system, right? I'm sure many of you are familiar with the term, but the idea of having basically two refrigeration systems on top of each other, or two cycles, rather, doesn't have to be refrigeration. Here you have, for example, on the low side, the CO2, which is traditionally not as great at high temperatures, so that you keep that low condensing temperature there, and you're able to then use the advantageous volumetric heat capacity. And then you combine that with a high temperature ammonia stage, which despite challenges of the discharge of compressors, ammonia generally does better at higher temperatures than CO2. And you're able to then cascade them together. One other point here is this is also a schematic from 2003, right? So we're seeing this latest growth in CO2 and propane and ammonia. But a lot of this technology or concepts at least have been shown to work in the past. And actually for large scale refrigeration, ammonia is quite mature, right? For smaller systems, it's not as often used. So it can be tough to find compressors below, let's say, 100 kilowatts of cooling capacity. But in terms of concerns about leakage, about oil solubility and separation and things like that, the beautiful part of ammonia is we can leverage a lot of existing knowledge from the cold storage area if we want to get to broader acceptance here. So that can be a quite powerful tool that we're hoping to see safely further implementation of in the future. I mentioned as well, right, some of the transcritical CO2 systems can have a bit of a challenge having competitive coefficients of performance with hydrofluorocarbons at middle to high ambient temperatures. And a lot of that is due to the combination of a low critical temperature and a high critical pressure, right? But with that being said, some work that was done at the TU Dresden did a beautiful job of highlighting a range of performance enhancing measures such as parallel compression, ejectors, which is a form of expansion work recovery, which again kind of utilizes that same disadvantage, if you will, of the large delta P between the high and low side of the system to reduce the amount of work a compressor needs to put in. External subcooling here, you can use a different working fluid. For example, we've seen that done also with small water-based air conditioner systems. And that'll then give you a larger enthalpy of evaporation or a larger cooling capacity for a given compressor power input. And then maybe one of the highest thermodynamic levels is the expansion work recovery device, where you're able to then capture a significant amount of those losses associated with the expansion process to have meaningful COP benefits on the order of up to 20% was reported in some of this work. So then when we think about those different systems, right, that was only one example here. Here's kind of a high level perspective showing what all these bells and whistles can actually do for a system's efficiency. You can see then the COP improvement from a range of different systems, ranging from the order of 5 to 7%, all the way up to mid-30s, depending on the operating conditions and systems, such that the annual energy savings may be slightly more meaningful. But again, this is a nice overview of some of the literature, more or less validating some of these concepts for CO2 systems. One of the last things I want to leave you all with is the legislation around the world can get a bit I would say overwhelming in terms of what happened when. So what I did is I kind of highlighted from 2010 from a refrigerant standpoint. You see there that the Montreal Protocol then reached one of its final stages, being the developed countries eliminate 90% of their HCFC production. I highlight this here because that was agreed upon in 1987. So it shows how long these different phases can truly take to reach full power. And that's been, to me, one of the best examples of effective legislation in this phase. Then, of course, you have Kigali, the EU F-gas, the second of now 3 F-gas regulations, right? The EPA SNAP allowing for hydrocarbons, which Jiwon also mentioned, Jiwon mentioned about the isobutane refrigerators, for example. The EPA AIM Act, which then began to approach the F-gas regulation at that time, still behind a little bit, but not too far. Then the MAC directive for the EU, right? This was largely responsible for 134A and YF and all of that discussion that's going on right now. And then, of course, the F-gas regulation update has been something that's been, I believe, the 3rd iteration there that's come into power now and is even more stringent than the first 2. Then, of course, the 2023 discussion by the ECHA. PFAS is not within the scope here, but the fact that that was then proposed in 2023, recently updated in August of this year, and goes up for comment in 2026. That's something to also keep our eye on. But I would suffice it to say that between 2020 and 2027, I would encourage you to just dive in to understand this various applications, because for different classifications, different applications, and so on and so forth, there are a range of limitations ranging from 150 to 750. So with that being said, again, some of the key points to leave you with, of course, if increasing system efficiency is unavoidable and needs to remain the top priority. With that being said, the direct refrigerant leaks and direct emissions resulting from that should also be addressed through lower GWP working fluids, keeping an eye on what happens with hydrofluoroolefin implications environmentally. And then also, of course, looking at the timescales for different regions around the world, which tend to head in the same direction, albeit with different velocities. And also making sure that discussions between experts, policymakers, and industry around the world are all able to maintain on the same level to make sure we're all pulling on the same string. So with that being said, I'd like to thank you very much for your time, and I look forward to the Q&A session following Katja's presentation.
Thank you very much, Relay, and thank you for highlighting the challenges and for supermarkets and large refrigeration systems, and for speaking about the hydrocarbons and the safety discussion. And that will be a topic of one of our webinars that will be coming in 2026. So to all the attendees here, keep an eye on our communication channels. We'll be having a webinar just to speak about the hydrocarbons. Finally, I will turn to Katja Klinar, Assistant Professor and Chair of Thermal and Environmental Engineering at Ljubljana University, Slovenia. And she'll be talking about solid-state refrigeration technologies and their scalability, which was slightly mentioned by Professor Juan in the beginning, but now we'll be getting a bit deep dive for the next 5 minutes to 7 minutes. Katja, please keep a pace of speaking that is reasonable for the live interpretation, because we have a team of live interpretation to French. So yeah, over to you.
You. Hello, everybody. My name is Katja Klinar, and today I'll briefly introduce the emerging technologies in refrigeration, why we need them, what they are, and where they can realistically replace or complement vapor compression cooling. So let me begin with the first question. Why do we need alternatives? The three graphs here show key performance characteristics of currently available cooling technologies, their COP, and the total power density based on the mass of the device or mass of the refrigerant. Vapor compression technology dominates the market, and most of these data points in these plots correspond to it. However, despite of its long-standing success, we are facing several pressures, so to say. The first one is the environmental concern. Sorry, I forgot to delete the animation. So the first one is environmental concerns. As already mentioned earlier today, even low GWP refrigerants still pose challenges in terms of leakage, recovery, and life cycle impacts, and regulatory requirements continue to tighten. Then the second pressure is the efficiency. So vapor compression systems are approaching both the thermodynamic and material limits, meaning that further performance improvements are going to be costly and incremental. And it's also important to highlight that at small cooling capacities, the efficiency is notably smaller. The third one is the temperature range. Vapor compression operates between roughly -100 and +300 degrees. Sorry, I apologize. Applications outside this range, so below -100 and +300, also require cooling solutions, yet vapor compression cannot meet those demands. So these factors combined motivate the exploration of emerging refrigeration technologies, the approaches that can complement existing systems, or in some cases, eventually replace vapor compression. There are different promising emerging approaches, the technologies, and they are based on different physical principles. I don't have much time, so I will just briefly introduce the most important ones, and then during the Q&A session, I can answer some more detailed questions. So the first group of solid-state refrigeration technologies are the caloric technologies. So these are magnetocaloric, electrocaloric, and mechanocaloric technologies. All these technologies exploit caloric effect in solid materials. In magnetocalorics, this effect is introduced by magnetic field change. In electrocalorics, by electric field change, and in mechanocaloric, by the change of force or pressure. So these technologies have been already actively researched for the last 20 years, and many prototypes have been built across the world. I would like to emphasize that these technologies already began their path towards industrialization. So here you can see some of the companies, which are mostly startups, that have already launched initial devices or produce the material. Another more novel technology, the thermoelectrics, which is based on the Peltier effect, is already well known, and a lot of companies are selling either the modules or already the devices, but I decided to include it in the emerging technologies also, because only recently heat pumps are becoming more and more interesting. And like in the previous presentation, you already saw one example of wine cooler, which is based on thermoelectrics. And the last technology that I would like to mention today is thermoacoustics. So thermoacoustics uses acoustic waves to transport heat. And recently, two startups started to design the devices. So these technologies have different advantages. I would prefer not to read all this, but we can discuss this in the Q&A session. And we also have challenges. So the challenges of these technologies are divided on the material challenges and device challenges. Again, I can discuss these challenges more in the detail during the Q&A session. So the third question and the last question I would like to address today is the application. Of course, these technologies will not replace vapor compression across the board. Instead, we expect phased adoption. So in the near term, they are most likely to appear in hybrid systems, like for cooling of electronics or waste heat-driven applications. And these are the places where their strengths provide immediate benefits. Then, in the medium term, we may see partial substitution in specialized equipment, such as medical devices, lab refrigeration, or portable appliances. And then in the long term, some technologies could fully replace vapor compression in niche segments where silent operation without vibration, high reliability, or the elimination of refrigerants is critical. And with this, I would like to finish my presentation. Thank you for your attention.
Thank you very much, Katja. Thank you for being brief. I know there is many very interesting and important things to discuss, but yeah, maybe we'll discuss it more in the Q&A session. So now the floor is open for all the attendees for questions. Please don't hesitate to copy paste it, to write your questions in the Q&A. And we'll start with the first question. I think there is a question. Is it possible for an oil-free compressor to be optimal with any type of refrigerant?
So let me give an answer to these questions. It's very important questions. Well, the oil-free compressor is usually already available for the chillers. I mean, the centrifugal compressors And in that systems, they already use the gas bearing concept, so they don't use oil. And another, the system is refrigerators. So domestic refrigerators, usually I mentioned that isobutane and R134A are used. For this refrigerant, oil-free compressor is working very nice. So, but already it's available. However, the problem is that the durability is not validated yet. So some companies, actually, the second question was that who are producing oil-free compressors? So it's connected. So to my understanding, many compressor manufacturers like Embraco and also LG Electronics in Korea, they are producing oil-free compressors for the household, the refrigerators already. But at this moment, they are distributing in a limited range because they wanted to know a kind of field test concept. Okay, so they are working good up to now, but they are still want to make it clear that there will be absolute no problem, and then they will be released in across every range. Hopefully, this can be an answer to these two questions.
Thank you, Professor Jong. Now a question to Riley. What is the typical charge for a R290 standalone display cabinet?
Most of them fall right below the legislative limit, as you might expect. So the smaller ones, like a bottle cooler, they land around 140 to 145 with isobutane usually. But if you get to the propane systems, for the larger systems, they're generally around 300 grams, which then falls below the 350 to 500 range, based on my experience. Of course, there are lots of variation there, but those are some order of magnitude numbers.
Thank you. A question that is not addressed to a specific speaker, but why we don't see more ammonia components for small-scale systems, at least slowly? I think that's Professor Jong.
Actually, I didn't see the ammonia systems for the domestic application. Maybe it's simply because ammonia has a good thermodynamic property as a refrigerant. However, it's a kind of safety issues. I mean, so it's kind of toxicity of ammonia. So in Korea, some these big cities doesn't allow use the ammonia as a fluid in for public places. So if this kind of ammonia is used for the household refrigerators, maybe some manufacturers are worrying about the toxicity. So that's why maybe there is no the refrigerators working on the ammonia.
Thank you very much, Professor. Now the question for Katja, and now you have time more to deep dive in the emerging technology topic. And the question is, how much time can we expect for these emerging technologies to be competitive?
This is a good question. So when I started working in this domain 10 years ago, everybody said that between 5 and 10 years, these technologies will be on the market. So now, 10 years later, we still say 5 to 10 years because there's a lot of challenges that need to be solved. There's a lot of progress. Like I showed the startups companies that already produce the demonstrators or the devices that you can actually buy and use. But yeah, so far they are not. It's difficult to say when exactly we will have in the market vapor compression refrigerators, and then next to them other technologies. It's yeah, let's say 5 to 10 years, but
we are working on it.
Yeah, definitely. We are working hard on it.
Great. A following question to the first one. In solid state cooling, 3 technologies, magneto, electro, and mechano suitable for high ambient operating conditions?
Yeah, so all these 3 technologies are also based on the phase change, but it's solid phase change. So what we need is the solid material, which has this solid phase change in the temperature range the device needs to operate. So there are materials from almost 0 degrees to, let's say, 1 or 1500 degrees Celsius. So with choosing the appropriate material or a combination of this material, we can make the device operate at the certain temperature range.
Okay. Another question. I think it's a very interesting topic for our audience. For you again, Katya, for very low and very high temperatures, we could also use gas cycles, which have been used for a long time. Could you comment on this?
Yeah, the gas cycles are established technology, so I didn't include them in the emerging part. But yeah, they are good technologies and already used in, like Professor Palm said, at lower and at higher temperatures.
Super. What is the typical COP of alternative cooling systems you were talking about?
It depends on the operating temperatures and on the conditions where the devices are designed. So for the prototypes, usually the COPs are, let's say, up to 3. But for these devices that are, let's say, products of these companies, that are actually the devices that operate in realistic, let's say, environment or conditions, it's, let's say, between 1 and 2.
Thank you very much.
It's lower than vapor compression so far,
Okay.
but we are improving.
Super. A question, is there any chance to see water as a refrigerant?
Is this still a question for me?
No, it's for all the panelists.
Okay, in emerging technologies, yes, we use water.
So even in conventional systems, the water is already being used in a lithium bromide, the absorption systems. So that kind of system is used for the building and air conditioning.
There was also a small, actually fairly successful attempt, although the company went under, for about a 25 kilowatt air conditioning system with turbo machines with water. But the volumetric capacity is just a really big problem to get the throughput there. So it's finding more and more use in high temperature heat pumps with multi-stage turbo or spindle compressors.
Thank you very much. The final question, what are the maintenance requirements for natural refrigeration compared to traditional ones? And would it be viable in, for example, aquaponics, farm-controlled environments?
Yes, I'm not sure exactly about the end application there. I'd imagine that had very unique challenges. But honestly, I don't know of too many differences in terms of the actual maintenance requirements. I would say for CO2, if you do need to go to stainless steel, sometimes the application there can be tough to find installers that are qualified. Some of the fittings may be a bit more prone to leaking, although with 25% leak rates of HFCs, you can't do too much worse than that in some respects. And then if you have a hydrocarbon with secondary loop, then you have to worry about the composition of the secondary loop, fittings, and plastic lines. But in general, I would say a well-installed system there shouldn't have any real maintenance differences as long as the design is done prudently.
Thank you very much. A final question to Katya. What is the potential of solid-state cooling to cool down processors in IT or computing applications?
Yeah, there is potential, but currently the majority of the devices operate at room temperature. So for the specific application, the right material would need to be chosen, and then the whole device would need to be designed to efficiently work in these temperature ranges. But yeah, it's possible.
Thank you very much. I would close the Q&A session. Thank you very much for this very engaging questions that varied from refrigeration, refrigerants, applications, and new applications. Thank you for the speakers for your time, for the presentation, and for answering all the questions. Now we move the floor to Dr. Yusra Alouche, which is she's the Director General of IIR, to share closing remarks and next steps of the publications co-jointly published by IIR and UNEP Ozone Action. Over to you, sir.
Thank you. Do you hear me?
Yes.
Yeah, okay. Thank you very much, Suhir. If you can please move the slide, I'm not able to do. For me, okay. Okay, thank you, Suhir. Just to wrap up, I think it doesn't need any introduction here. Cold chains, we know it's essential for keeping our food temperature-sensitive products safe from the production all the way to the consumer. And we have been speaking today about the domestic refrigeration, the commercial alternative technologies. The message here is that we need to know that it's not the importance is not only about lowering the temperature, but also the challenge is about to maintain it and to reduce the fluctuations, which comes with some challenges in maintaining consistent temperature, reducing energy use, balancing reliability and sustainability. So these are like constant concerns. And also beyond the energy performance, we need to note that food safety is also of concern. As studies, they show that about 1/3 of products, they exceed recommended temperatures. So simple solutions like closed doors cabinets, as Riley has mentioned earlier, instead of the open designs, they can make a real difference in keeping the temperature stable. Next, please. Thank you. Challenges, they are here, but when we say challenges, we say also opportunities, and energy efficiency is one of the key solutions. So Professor Huang here was speaking about opportunities for energy efficiency, new design of heat exchangers, working on insulations, but also new system configuration like the dual loop systems for domestic refrigeration, which gives 12% of the reduction of energy consumption, knowing that we have 2.2 billion refrigerators in the world. He was also speaking about oil-free compressors to improve the heat transfer efficiency. Riley also was referring to the various configurations for supermarkets, energy saving through actually very basic operations as installing doors, but also that can reduce actually, according to IR numbers, up to 70% of the energy consumption. Applying overfed evaporators to increase the evaporator temperature and also to increase the suction pressure of the compressor. Applying parallel compressors to support the load on the main compressor and the potential for CO2 systems for heat recovery as well. So technology is there. It's being demonstrated in terms of refrigerants also. So we have seen the potential of natural refrigerants and low GWP refrigerants as well. So in all the applications. And then another message that I would like here also to convey from an IR perspective is that it's not only about technology, it's also coordinating efforts at a national level, including energy efficiency efforts with the refrigerants efforts, but also extending beyond these applications to include food actors, health services, logistics is essential as the refrigeration sector is transversal and touching many different areas. And then an IIR perspective as well is to adopt an integrated approach, including all refrigeration cold chain actors to accelerate the transition to sustainable refrigeration. Next, please. So for that, I would like to also to thank you first for attending this webinar on this first communication of the cold chain, and I would like to invite you to the next webinar on marine refrigeration, keeping the catch cool from sea to shore, which will take place on the 25th of November at 2 p.m. So you can scan this QR code to subscribe. And then another webinar about refrigerated transport in hot climates, challenges and innovation. You are very welcome also to subscribe here, scanning this QR code, which will take place on the 9th of December at 2 p.m.
Thank you very much. Yeah.
No, we still
yeah.
have,
Oh, yeah.
I won't miss this opportunity to invite you
Of
all
course.
also to scan these QR codes and participate to next IAR conferences. So ThermMag conference. So Katia was speaking about emerging technologies and solid cooling states. So that's the perfect place to learn more about these emerging technologies. It will be on the June 7 to 11 2026. And then we have Gustav Lawrenson conference on natural refrigerants in August 2026 in New Zealand. And then phase change materials or PCM 2026. And here Rayleigh also was speaking about importance of cold storage using phase change materials in China in September 16 to 18. Last but not the least, I would like to invite you all to welcome you to the International Congress of Refrigeration 2027 in Korea. So that's the flagship event of IR, which has already started since 120 years earlier. So you are very welcome to scan this QR code and also join us in this very important IR event in 2027. Thank you very much.
Thank you very much, Yosef. Thank you to all the speakers. Thank you, Jim, and to Authors on Action for this excellent partnership on communicating the cold chain technology briefs. Keep an eye on IAR communication channels for the next webinars, LinkedIn, newsletters, and website. See you on the next webinar, and thank you all for your time. Bye-bye.
Thank you.
Thanks, everyone.
Thank you. Bye.
Thank you.
Yeah, bye-bye.
Bye.
Bye.
Thank you very much.
Thanks to the speakers.
Thank you.